The oldest photograph of our universe reveals its fiery birth. This is the cosmic microwave background, the ancient light that has traveled for over 13 billion years to reach us. By the end of this journey, you will see the cosmos through an entirely new lens. We will uncover how this faint glow exposes the universe's original blueprint and holds the secrets to its darkest mysteries, from invisible matter to its ultimate fate. How can a whisper of cold radiation tell us where everything came from and where it is all going? For nearly 400,000 years, the universe remained in this state of brilliant confinement. Light was a prisoner, bouncing endlessly in a hot, soupy fog of plasma. But then something monumental happened. The cosmos expanded and cooled just enough, dropping below a critical temperature. This was the moment of recombination. For the first time, protons and electrons could combine to form stable, neutral hydrogen atoms. Think of a chaotic, crowded room suddenly falling silent and orderly. In that instant, the fog lifted. The particles that had been constantly blocking light's path simply stepped aside, and with that, the universe became transparent. That first flash of liberated light, unleashed in every direction at once, is the very same ancient glow we detect today as the cosmic microwave background. It was the universe's very first photograph, a snapshot of its own fiery infancy, and that canvas of ancient light holds the imprint of everything that came next. This ancient photograph is a fossil of light, but what exactly are we looking at? The cosmic microwave background is not a simple glow. It is a nearly perfect blackbody spectrum. Think of the pure, predictable light emitted by a perfectly hot object, like the red-hot element on a stove. The universe, in its infancy, was just such an object, and it imprinted this perfect thermal signature across the entire sky. Today, that radiation has cooled to an almost unimaginably cold temperature of just 2.725 Kelvin. That is merely a few degrees above the coldest temperature possible, absolute zero. This cold whisper fills every cubic centimeter of the space around you, a relic radiation field that is the cooled-down remnant of the universe's fiery birth. But its most profound secret lies not in its uniformity, but in its imperfections. Superimposed on that near-perfect cold blanket are the tiniest of variations, minute differences in temperature known as anisotropies. These fluctuations are incredibly subtle, on the order of just 1 part in 100,000. To grasp that scale, imagine a completely smooth, flat beach that stretches for miles. The most significant feature on that entire beach would be a single grain of sand lifted barely a millimeter above the rest. These tiny wrinkles are the most important part of the entire signal. They are the imprints of the primordial over densities and under densities in the early cosmos. Slightly hotter spots mark where matter was just a little more packed together, and slightly colder spots where it was a little more sparse. These minute differences in density acted as gravitational seeds. Over billions of years, gravity amplified these tiny imperfections, pulling more and more matter toward the denser spots. The great cosmic structures we see today, the vast web of galaxies and galaxy clusters, all grew from these microscopic ripples. The cosmic microwave background is the universe's unique fingerprint. Every swirl and ridge in its temperature map tells a part of the story, a coded message from the very beginning that we are only now learning to read. Those tiny ripples in the cosmic background were not our first clue to its existence. The story of its discovery is a masterpiece of scientific serendipity. In 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were working with a massive, sensitive horn antenna in New Jersey. Their goal was to study natural radio waves from our galaxy, but their work was constantly frustrated by a persistent, unexplained hiss. It was a uniform microwave noise that came from every direction in the sky, day and night, and it would not go away. They were meticulous. They checked every possible source of interference. They even discovered that a pair of pigeons had been nesting inside the giant horn, and they carefully cleaned out the droppings, which they jokingly referred to as a white dielectric material. Yet even after the pigeons were evicted, the maddening hum remained. This was not a product of a faulty instrument or local interference. It was something real, and it was coming from deep space. At the very same time, a team of physicists at Princeton University, led by Robert Dick, was actively building a detector to find this very signal. They had predicted that if the Big Bang model were correct, a faint, cool glow should still permeate the entire universe. When Penzias and Wilson heard of this work, they realized the truth. Their annoying background static was not a technical flaw. It was the echo of creation itself, the cooled remnant of the universe's fiery birth. That persistent hiss was the cosmic microwave background, for stumbling upon the oldest light in the cosmos, a discovery they were not even looking for. Penzias and Wilson were awarded the Nobel Prize in Physics. This accidental finding provided the first direct, irrefutable evidence for the hot Big Bang model, transforming our understanding of the universe from a speculative theory into a concrete chapter of our cosmic history. Penzias and Wilson had found the signal, but its true picture remained hidden for decades. It was a uniform hiss, a cosmic sea of sameness. The challenge was monumental. How do you map the whisper-fine wrinkles on this ancient canvas from the noise of our own galaxy and the limits of our instruments? The answer arrived in a satellite named COBE, the Cosmic Background Explorer. In 1992, after years of painstaking data collection, the COBE team unveiled the first ever full sky map of the cosmic microwave background. The image was breathtaking. It showed a universe of almost perfect uniformity, a brilliant confirmation of the Big Bang's core prediction, emblazoned across the entire sky. But then the scientists looked closer. Etched into that smooth, cold sea were the faintest possible ripples. These were the anisotropies, the minute temperature variations cosmologists had been searching for. They were tiny, just 1 part in 100,000, but they were real, and they were everywhere. George Smoot, the project's lead scientist, captured the awe of the moment when he described the map as like seeing the face of God. It was a poetic expression for a profound scientific truth. For the first time, humanity was staring directly at the blueprint of the cosmos. Those tiny hot and cold spots were the gravitational seeds from which all structure would grow. The subtle overdensities, the places where matter was ever so slightly more packed together, were the very spots where, over billions of years, gravity would patiently pull, forming the first stars, the first galaxies, and the vast cosmic web we see today. COBE did not just take a picture. It provided the universe's original recipe, proving that the potential for everything, including us, was written into its fabric from the very first moments. COBE gave us the universe's blueprint, but the lines were still blurry. The next leap in precision came from a silent sentinel named the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, its mission was to stare at the cosmic background with a clarity we had never before achieved. For 9 years, WMAP meticulously charted those minute temperature variations, transforming the faint whispers of the early universe into a clear, quantitative voice. It measured the anisotropies with such exquisite detail that it allowed cosmologists to pin down the fundamental properties of our cosmos with an accuracy of better than 1%. Imagine trying to measure the exact dimensions of a room with a long, knotted rope. COBE gave us the rope, proving the room existed. WMAP untangled every single knot, giving us a perfect, precise measurement. It told us the universe is 13.77 billion years old, not roughly 14 billion, but with a specific, known birthday. It precisely quantified the cosmic recipe, revealing that the familiar atoms making up stars, planets, and us account for less than 5% of the total content. About 25% is the mysterious gravity-influencing dark matter, and a dominant 70% is the even more enigmatic dark energy, the force accelerating the universe's expansion. Perhaps most profoundly, WMAP confirmed the universe's geometry is flat. Not flat like a sheet of paper, but flat in the sense that parallel lines never meet, and the rules of Euclidean geometry we learned in school hold true on the grandest of scales. WMAP single-handedly transformed cosmology from a field of broad, competing theories into a precise, quantitative science. It gave us a standard model of the universe, a quantitative blueprint of cosmic origins, all read from the subtle patterns in the oldest light we can see. If WMAP gave us a precise blueprint, then the Planck satellite performed a forensic analysis. Launched by the European Space Agency, this advanced observatory spent 4 years, from 2009 to 2013, scanning the heavens with an unprecedented eye for detail. Its mission was to observe the cosmic microwave background with a sensitivity and resolution that dwarfed all prior efforts. Planck did not just look at the temperature of the ancient light, it peered into its very polarization, measuring the specific direction in which these primordial light waves vibrate. This is like moving from a black and white photograph to a high-definition, three-dimensional movie, revealing the dynamic forces at play in the universe's first moments. Planck's incredible data overwhelmingly confirmed and refined the cosmic recipe WMAP had provided, sharpening our numbers to a razor's edge. Yet, it was in the subtle, unexpected details that Planck truly shook the foundations of cosmology. The map it produced was not perfectly uniform in the ways our theories predicted. It revealed strange cosmic anomalies. One was a mysterious cold spot, an area of space significantly chillier than the surrounding background, far larger than our models can easily explain. Even more puzzling is a fundamental asymmetry, a lopsidedness in the temperature fluctuations across the sky. One half of the universe appears to have slightly more pronounced wrinkles than the other. Think of a seemingly perfect round soap bubble that, upon the closest inspection, has a subtle but definite flat spot on one side. These are not mere curiosities. They are genuine cosmic puzzles that challenge the standard model of cosmology, the very framework we use to understand everything. They whisper of physics beyond our current understanding, suggesting that the universe's first chapter may contain plot twists we have not yet dreamed of. The oldest light is not just an echo of the past, it is an active conversation pointing toward mysteries that lie just beyond the edge of our current knowledge. Those strange cosmic anomalies are not the only secret hidden within the ancient light. This faint glow also contains the frozen echo of the universe's very first sound. In that primordial plasma, before atoms could even form, the cosmos was a roiling, chaotic sea. Two fundamental forces were locked in a constant, rhythmic battle. On one side was gravity, relentlessly trying to pull the hot particles of matter together. Pushing back with immense force was radiation pressure, the intense energy of light itself, trying to blast everything apart. This cosmic tug-of-war created powerful, spherical pressure waves that rippled outwards through the infant universe. These were sound waves, traveling at an incredible fraction of the speed of light through a medium far denser than any solid. For nearly 400,000 years, these acoustic oscillations pulsed through the cosmos, a deafening symphony of creation. Then, the moment of recombination happened. The universe became transparent, the music stopped, and the waves were instantly frozen in place. Imagine a recording of a single, powerful chord, suddenly paused and preserved for all time. That is the Baryon acoustic oscillation. This frozen wave left a distinct ring-like pattern imprinted on the cosmic microwave background. In the temperature map, we see it as a faint preferred scale, a subtle circle where matter is slightly more concentrated. This fossilized sound wave acts as a cosmic standard ruler. We know its true physical size from our understanding of the early universe's physics. By then measuring how large or small this ruler appears to be on the sky, we can perform a direct geometric measurement of cosmic distances. It is like finding a coin of known size embedded in a photograph and using its apparent size to calculate how far away the camera was. This single, frozen ripple connects the universe's infancy directly to its present-day structure. The same preferred scale we see in the ancient light is also visible in the vast modern cosmic web. The distribution of galaxies today shows a subtle statistical preference to be separated by the exact same distance as the rings in the background radiation. This means the blueprint for the placement of galaxies, including our own Milky Way, was set by those primordial sound waves in the first moments of time. The Baryon acoustic oscillation is a direct link, a bridge of unimaginable scale, connecting the whisper of the Big Bang to the grand architecture of the cosmos we inhabit today. That frozen symphony of sound waves does more than just map the cosmos. It acts as a cosmic ledger, meticulously recording the universe's entire budget of energy and matter. Every subtle wrinkle and ripple in the background radiation is a data point, a clue that allows scientists to weigh the components of our reality with astonishing precision. The results are profoundly humbling. The ordinary atoms that form everything we can see and touch, from the stars in the sky to the planet beneath our feet, account for a mere 5% of the total cosmic pie. This is the luminous universe, and it turns out we are the exception, not the rule. The remaining 95% is composed of two profound and invisible mysteries. Roughly 27% is dark matter, an enigmatic substance that does not emit, absorb, or reflect any light. We cannot see it, but we know it is there because of its immense gravitational pull. It is the invisible scaffolding that holds galaxies together, a cosmic skeleton without which the universe would look entirely different. The dominant force, making up a staggering 68% of the cosmos, is dark energy. This is not matter at all, but a repulsive force inherent to the fabric of space itself, a pressure that is causing the expansion of the universe to accelerate. The patterns in that ancient light are so precise that they allow us to calculate this exact recipe. The cosmic microwave background does not just describe the universe's birth, it delivers a complete and startling inventory of its contents, revealing that the familiar world of planets and stars is merely a thin shimmer on the surface of a much deeper, darker, and more mysterious ocean. This flat geometry is not just a mathematical curiosity, it is a cosmic necessity written into the very first light. The pattern of hot and cold spots in the cosmic background acts as a built-in protractor for the universe. Think of those spots as standard-sized measuring rods. In a closed, spherical universe, these spots would appear larger to us, their light paths bending along the curved space. In an open, saddle-shaped cosmos, they would appear smaller, but when we measure them, the spots appear exactly the size predicted for a perfectly flat geometry. The data from satellites like WMAP and Planck leave no room for doubt. We live in a flat universe where the rules of geometry we learned in school, that parallel lines never meet and the angles of a triangle always add up to 180 degrees, hold true across the entire observable cosmos. This profound flatness solves one of cosmology's oldest puzzles. For the universe to be as flat as we observe it today, its initial conditions had to be fine-tuned to an absurdly precise degree, like balancing a pencil on its tip for billions of years. This seemed like an unbelievable cosmic coincidence until the theory of inflation provided the answer. Inflation proposes that a fraction of a second after the Big Bang, the universe underwent a brief, violent burst of exponential expansion, inflating by a factor of trillions upon trillions in a mere instant. This hyper-expansion would have stretched the fabric of spacetime itself, ironing out any primordial wrinkles or curvature, just as blowing up a balloon to an immense size makes its surface appear locally flat. The perfect flatness we measure is the most compelling evidence we have that this incredible inflationary event truly happened, smoothing the cosmic canvas to the pristine geometry we observe today. This perfect uniformity presents one of the deepest puzzles in all of cosmology. When we look at the cosmic microwave background, the temperature is the same everywhere to an astonishing degree of precision. Regions on opposite sides of the sky, billions of light-years apart, are synchronized to within 1 part in 100,000. But according to the standard Big Bang model, this should be impossible. There is a fundamental speed limit in the universe, the speed of light, and in the 13.8 billion years since the Big Bang, light has only had time to travel a finite distance. This creates what is known as our observable horizon. Now picture two scientists standing back to back, each looking out to the very edge of the observable universe in opposite directions. The patches of sky they are observing are so far apart that a beam of light leaving one region at the moment of the Big Bang would just now be arriving at our telescopes, and it would have had no time whatsoever to continue on to the other region. Those two distant parts of the cosmos have never been in contact. They have never exchanged a single photon or communicated in any way. How then can they possibly know to be at the exact same temperature? It is as if you met a perfect stranger from the other side of the world, and you both discovered you were wearing identical outfits, down to the same color of socks, without ever having spoken. This is the horizon problem, a paradox that suggests the early universe was somehow in perfect sync without any physical mechanism to explain how that coordination happened. The most elegant and powerful solution is a theory called cosmic inflation. This idea proposes that in the very first fraction of a second, a tiny, subatomic speck of the primordial universe underwent a violent, exponential growth spurt. In less than a trillionth of a second, this infinitesimally small patch expanded faster than the speed of light, stretching by a factor of at least 10 to the 26, to become larger than our entire observable universe today. Before this inflation, that entire tiny patch was causally connected. It was a single, cozy room where every particle could interact and easily equalize its temperature. Then inflation acted like a cosmic magnifying glass, taking that one small, uniform region and stretching it to become the entirety of the cosmos we can see. The entire sky was once a single, connected point, which is why it appears so uniform today. The horizon problem vanishes because the two distant sides of the sky we see today were once intimately linked, neighbors in a microscopic realm before being blown apart to opposite ends of creation. This theoretical hyper-expansion, known as inflation, solves the cosmic puzzles with breathtaking elegance. The mechanism behind this incredible growth spurt is a hypothetical energy field that permeated the infant cosmos, known as the inflaton field. For a fleeting fraction of a second, this field possessed a peculiar property. It generated a repulsive form of gravity, an anti-gravity that pushed the fabric of space itself apart with unimaginable force. This is not matter moving through space faster than light, which is forbidden, but space itself stretching faster than light, which is perfectly allowed by physics. This violent, exponential stretching is what ironed the universe to perfect flatness and took a single, connected region and blew it up to become our entire observable cosmos, elegantly explaining the horizon problem. But inflation's greatest gift was not just solving old puzzles, it was creating the seeds for everything to come. During this frantic expansion, the inflated field was not perfectly smooth. It was fizzing with quantum mechanical vibrations, tiny, random fluctuations at the smallest possible scale. As space inflated at a staggering rate, it stretched these microscopic quantum jitters, magnifying them to a cosmic scale. Think of a tiny, microscopic wrinkle on a balloon. As you blow the balloon up to the size of a house, that tiny wrinkle becomes a massive, continent-sized ripple. In the same way, inflation took quantum uncertainties and imprinted them across the entire universe as minute differences in density. These are the primordial fluctuations, the very same hot and cold spots we see in the cosmic microwave background. The specific statistical pattern of these spots, their size and distribution, is a perfect match for the predictions of inflationary theory. The ancient light does not just suggest inflation happened, it bears its unique signature, a fingerprint left by quantum mechanics magnified to a cosmic scale, providing the initial push that gravity would later use to build the entire visible universe. The grand cosmic web, with its galaxies and voids stretching across billions of light-years, did not emerge from nothing. Its origin is perhaps the most profound connection in all of physics, a bridge between the impossibly small and the unimaginably large. Those subtle density variations frozen into the cosmic microwave background were not placed there at random. They are the amplified echoes of quantum noise, the inherent jitteriness of reality itself at the smallest scales. This is governed by the Heisenberg uncertainty principle, a fundamental rule of the quantum world which states that even in a perfect vacuum, empty space is never truly still. It is a seething, bubbling foam where pairs of virtual particles spontaneously pop in and out of existence. On their own, these quantum fluctuations are vanishingly small and last for only an instant. But they occurred at the precise moment when the universe was undergoing its violent inflationary growth spurt. As space expanded faster than light, it stretched these subatomic tremors, locking them in and magnifying them from the quantum realm to a cosmic scale. A quantum ripple that was smaller than a single atom one moment could, after inflation, be larger than an entire galaxy cluster. These magnified ripples became the slight over densities and under densities in the primordial plasma, the very same hot and cold spots we now read in the ancient light. This means the distribution of galaxies we see today, the very location of our own Milky Way, was ultimately determined by a random quantum fluctuation in the first trillionth of a second of time. The cosmic background is therefore far more than a fossil. It is a direct photograph of quantum mechanics written across the sky, a permanent record of the moment the quantum world became the cosmic one. Every structure we see is the grown-up version of a microscopic tremor, revealing that the universe's largest architectures were seeded by its smallest possible vibrations. But temperature is only half the story painted by that ancient light. The cosmic microwave background also carries a hidden signature in its very orientation, a property known as polarization. This means the electric field of this primordial light does not vibrate randomly in all directions. Instead, it has a subtle preference, a specific alignment imprinted upon it during its final interactions with matter. This polarization comes in two distinct patterns, which scientists call E modes and B modes. The E mode pattern is relatively straightforward. It was created when the light from the infant universe was scattered for the last time by the clumps of ordinary matter, the same density fluctuations that create the hot and cold spots. This pattern looks like radial lines or spokes emanating from a central point, and it has been mapped in exquisite detail, confirming our picture of the early cosmos. The B modes, however, are an entirely different and far more elusive beast. Their pattern is a curling, swirly one, like the fingerprints of a cosmic giant. These faint swirls are a potential smoking gun for two of the most profound phenomena in cosmology. The first source is gravitational lensing. As the ancient light travels for billions of years to reach us, its path is gently warped by the gravitational pull of all the matter it passes, including the vast webs of dark matter. This warping subtly twists the light's polarization, converting some of the E mode pattern into a B mode pattern, creating a fossil record of the universe's entire matter distribution. The second and far more revolutionary source could be primordial gravitational waves. According to the theory of inflation, the universe's violent growth spurt would have shaken the very fabric of space-time, creating ripples in gravity itself that propagated outward. These waves would have left a unique, swirling B-mode imprint on the cosmic microwave background. Finding this specific primordial B-mode signal would be like discovering the fossilized ripples from the Big Bang's first tremor. It would be direct, incontrovertible evidence that inflation truly happened, and it would open a window into the universe at energies 1 trillion times higher than any particle collider can reach. This is the ultimate frontier in the study of the oldest light. Observatories at the South Pole, high in the Chilean Andes, and even in space are now hunting for these faint swirls, seeking the final confirmation of our cosmic origin story written in the polarization of the universe's first photograph. The hunt for these elusive B-mode swirls is a quest to witness the very first tremor of spacetime. Imagine trying to hear the faintest whisper in a roaring hurricane. That is the monumental challenge facing cosmologists. The signal they are searching for is incredibly weak, buried under the glare of our own galaxy's dust and the subtle polarization from gravitational lensing. The search reached a fever pitch in 2014 when the BICEP 2 telescope at the South Pole announced a potential discovery. The world of science held its breath. It appeared they had found the primordial B modes, the direct imprint of inflation, but further analysis using data from the Planck satellite revealed a heartbreaking truth. The swirling pattern was not from the dawn of time. It was foreground contamination, the polarized light emitted by ordinary dust within our own Milky Way galaxy. It was a sobering lesson in cosmic humility, a reminder of how many layers of interference stand between us and the universe's first moments, yet the search did not end. It intensified. The goal is so profound that failure only fuels greater innovation. New generations of telescopes, with even more sensitive detectors and better methods for filtering out galactic dust, are now scanning the skies from the high, dry deserts of Chile to the frigid plateau of the South Pole. They are trying to peer through the cosmic static to find that ultimate signature. A confirmed detection would be far more than just another data point. It would be a direct recording of the universe's violent birth cry, a vibration from a time when all of reality was smaller than a single atom. It would prove that inflation truly happened, and by measuring the strength of these gravitational wave ripples, scientists could directly calculate the energy scale of that explosive event. We would know with concrete certainty the incredible forces that forged our cosmos in its first trillionth of a trillionth of a trillionth of a second. This is the final frontier of the oldest light, a search for the faintest of swirls that would unlock the very first chapter of our cosmic story. The hunt for primordial swirls pushes us to the very edge of time itself, to a moment so early it defies our current physics. We can trace the history of the cosmos with remarkable clarity back to its first 380,000 years, thanks to the cosmic microwave background. But that ancient photograph is not the final page of the story. To uncover the true origins of everything, we must journey back even further into the universe's very first second. The ultimate frontier lies in the Planck epoch, the first 10 to the negative 43 seconds after the Big Bang. This is an era of almost mythical intensity, a duration so short it has no meaningful analogy in human experience. During this fleeting instant, the entire universe was compressed into a volume trillions of times smaller than a single proton. The energy density was so unimaginably high that the very concepts of space and time as we know them break down completely. At these scales, the smooth, geometric fabric of Einstein's general relativity collides with the fuzzy, probabilistic chaos of quantum mechanics. The force of gravity, which normally shapes galaxies and bends starlight, would have been just another quantum player fluctuating wildly. We currently have no theory, no mathematical framework that can successfully merge these two pillars of physics to describe what happened in that first flash of existence. This is the realm of quantum gravity, the final piece in our puzzle of fundamental forces, and it remains one of science's greatest unsolved problems. So how can we possibly hope to understand an epoch that our theories cannot even describe? The answer lies in the clues it left behind, frozen into the cosmic microwave background. The profound flatness of the universe, the specific statistical pattern of the hot and cold spots, the very existence of those primordial density fluctuations, all of these are direct consequences of physical processes that occurred during the Planck epoch and the inflationary burst that likely followed. The ancient light we detect today is the ultimate cosmic messenger, carrying encoded information from that first, unfathomable moment. By reading its subtle patterns with ever greater precision, we are using the universe's first photograph as a stepping stone. It guides our theories, telling us what a successful theory of quantum gravity must ultimately explain. The quest to decode the cosmic microwave background is not just about understanding the universe's infancy. It is a direct path toward a theory of everything, a single, elegant framework that could describe all forces and all particles, from the birth of spacetime to the formation of galaxies. The oldest light in the cosmos is our only tangible link to that mysterious dawn. The silent, invisible hand of dark matter left its signature all over that ancient photograph. We cannot see this mysterious substance, for it does not interact with light in any way, yet its immense gravitational presence was a dominant force in the early cosmos. Its influence is etched into the very statistical patterns of the hot and cold spots on the cosmic microwave background. To understand how, picture those primordial sound waves rippling through the universe's soupy plasma. They were pressure waves driven by the push of radiation and the pull of gravity. Dark matter, unaffected by the intense radiation pressure that pushed ordinary matter around, acted as a heavy, stabilizing anchor. Its gravity created deeper gravitational wells for the plasma to slosh in and out of, subtly changing the rhythm and amplitude of those cosmic sound waves. This altered the specific sizes and distribution of the hot and cold spots we observe in the CMB map. By measuring these patterns with extreme precision, cosmologists can perform a kind of cosmic accounting. They can calculate exactly how much gravitational mass was needed to create the oscillations we see. The result is clear and startling. Dark matter outweighs ordinary matter by a factor of about 5 to 1. It provided the essential, massive scaffolding upon which the visible universe could later assemble. Without this invisible gravitational glue, the slight overdensities in the early plasma would not have been strong enough to hold onto their matter. The radiation pressure from the intense light would have blown apart any incipient structures before they could even begin to form. Dark matter's gravity held the seeds firm, creating the stable environments where galaxies could eventually grow. The cosmic microwave background thus reveals a profound truth. The universe we see is built upon a framework we cannot see, a dark architecture whose blueprint is permanently recorded in the oldest light. That first flash of liberated light did not mean the universe's story was over. For millions of years after the cosmic background radiation was set free, the cosmos descended into a profound darkness. This was the cosmic dark ages, a time when the universe was a vast, featureless sea of neutral hydrogen gas. No stars had yet been born, no galaxies glittered in the void. It was a silent, unlit expanse waiting for a spark. Then, a few 100 million years after the Big Bang, the first generation of stars ignited. These were not like the stars we know today. They were behemoths hundreds of times more massive than our Sun, and they burned with a ferocious, brilliant, blue-white intensity. Their birth marked the end of the darkness. These first stars and the earliest galaxies that hosted them flooded the cosmos with an intense torrent of ultraviolet radiation. This powerful light began a second great transformation of the universe, an event known as reionization. Think of it as a cosmic dawn, not a gentle sunrise, but a sudden, searing flashbulb going off across the entire sky. The ultraviolet photons from these first stellar furnaces carried so much energy that they began to violently rip electrons away from the peaceful hydrogen atoms that filled all of space. The neutral gas that had made the universe transparent was now being torn apart, turned back into a free floating plasma of protons and electrons. But this new plasma was incredibly sparse, a thin, hot fog, not the dense soup of the early universe. It could not trap light again, but it could leave a final mark on the oldest light traveling through it. As the cosmic microwave background radiation continued its journey across the expanding universe, some of its photons passed through this newly reionized gas. The free electrons in this plasma scattered the ancient light one last time. This final interaction did not erase the primordial temperature map, but it did imprint a specific, large-scale pattern of polarization onto the CMB, what scientists call E-modes. This signal is a fossilized record of reionization itself. By meticulously measuring this specific polarization pattern, we can effectively carbon date the end of the cosmic dark ages. It tells us when the first luminous objects switched on and began flooding the cosmos with light, fundamentally changing the nature of the universe forever. That faint echo in the polarization is our direct line to that pivotal dawn, the moment the first stars ended the long night and began sculpting the transparent cosmos we call home. But the light we see is not the only messenger from the dawn of time. The Big Bang forged another, far more elusive kind of fossil. Just 1 second after the universe began, a cosmic sea of ghostly particles was set free. These are the cosmic neutrinos. Billions of them are passing through your body every second, utterly unnoticed, a whisper of the universe's violent birth. These neutrinos are so reluctant to interact with normal matter that they escape the dense plasma of the early universe a full 380,000 years before the cosmic microwave background was born. This makes the cosmic neutrino background the oldest fossil in all of creation, a relic from the universe's first heartbeat. We cannot see this neutrino sea directly. Building a detector to image it like we have for the CMB is a technological dream for the distant future. Their ghostly nature means they leave no simple, pretty picture for our telescopes. Yet we know they are there because their presence left a distinct scar on the light we can see. Think of the early universe as a crowded pool filled with a thick plasma. The photons of light were like people packed shoulder to shoulder, constantly bumping into each other and the surrounding matter. The neutrinos, however, were like sleek swimmers who immediately dove in and never touched the sides again. They streamed outward at nearly the speed of light, a vast, invisible tide. This great neutrino exodus had a profound gravitational effect. As they rushed away from over-dense regions, their collective gravity pulled matter along with them, subtly altering how the primordial plasma could slosh and ripple. This changed the statistical distribution, the specific power spectrum, of the hot and cold spots in the later cosmic microwave background. It is a tiny effect, a faint signature buried in the map's complex patterns, but it is detectable. By decoding this subtle imprint, cosmologists have performed a remarkable piece of cosmic archaeology. They have counted the number of fundamental neutrino families in the universe, confirming there are 3, and they have measured the C of these relic particles, confirming its role as a fundamental component of the primordial cosmos. The ancient light we see carries the shadow of an even more ancient particle, a fossil from the universe's very first second. Yet our most trusted cosmic relic now points toward a potential crack in this elegant model. This crack is known as the Hubble Tension, and it represents one of the most significant and stubborn puzzles in modern cosmology. The issue revolves around a single, crucial number, the Hubble constant. This is the current expansion rate of our universe, a value that tells us how fast galaxies are receding from us at any given distance. For decades, cosmologists have worked to pin down this number with ultimate precision. They have developed 2 brilliant, independent methods. The first looks at our local cosmic neighborhood. Astronomers use cosmic lighthouses, like pulsating stars called Cepheid variables and brilliant stellar explosions, known as Type 1, a supernova, to measure distances and velocities of relatively nearby galaxies. This gives us a direct, modern measurement of the expansion rate. The second method uses the cosmic microwave background as its starting point. By analyzing the precise patterns of the hot and cold spots in that ancient light, scientists can run the cosmic film backwards to understand exactly how the universe expanded from the Big Bang to today. This provides an extrapolated value for what the Hubble constant should be now. Both methods are the pinnacle of scientific precision, refined over years of painstaking observation. And they disagree. The local measurement gives us a faster, more frantic expansion rate. The CMB method, rooted in the pristine early universe, gives us a slower, more sedate one. The discrepancy is small, but it is real, and it persists even as our measurements become more and more accurate. This is not a case of a blurry photograph. It is like having 2 of the world's most perfect clocks, both impeccably crafted, ticking at stubbornly different speeds. This Hubble tension is more than a minor statistical fluke. It is a direct challenge, suggesting that something fundamental is missing from our cosmic recipe. Perhaps dark energy is not a constant, but an evolving force that has changed its strength over cosmic history. Maybe neutrinos have strange, unknown properties that alter the expansion story. Or perhaps there is an entirely new ingredient in the cosmos that we have not yet dreamed of. The ancient light, our guide for so long, is now pointing toward a horizon of unknown physics, hinting that the universe's greatest secret may be hidden in this tiny, persistent mismatch between its past and its present. The elegant solution of inflation might have opened a door to a reality far stranger than we ever envisioned. This cosmic stretching not only explains the universe we see, but also suggests the existence of countless others we cannot. This is the multiverse hypothesis, a staggering consequence of a theory called eternal inflation. The idea is that the inflattened field, the engine of our universe's initial growth spurt, may not have shut off everywhere at once. Instead, it could have only decayed into a stable state in our local patch, creating our Big Bang and our observable universe, while the rest of the meta-universe continues inflating at an exponential rate forever. In this eternal sea of hyper-expansion, random quantum fluctuations would constantly trigger the formation of new bubbles, new pocket universes, each with its own distinct Big Bang. Our entire cosmos, with its hundreds of billions of galaxies, would be just one bubble in an infinite, frothing ocean of reality. This is not a different theory. It is a direct extension of the inflationary model that so perfectly explains the patterns in the cosmic microwave background. The very flatness we measure and the specific fluctuations we map could be the local conditions of our particular cosmic bubble. So why does our universe seem so finely tuned for life? The values of fundamental constants, like the strength of gravity or the mass of an electron, appear perfectly calibrated to allow stars, planets, and ultimately us to exist. The multiverse offers a profound answer to this riddle. In an infinite landscape of universes, the laws of physics are not universal laws at all. They are just the local bylaws of our neighborhood. In other bubbles, these constants could have any random value. Most of those universes would be stillborn or chaotic, utterly incapable of forming complex structures. We, of course, find ourselves in one of the rare habitable bubbles, not because of design, but simply because we are here to observe it. This is the anthropic principle in action. The cosmic microwave background, then, becomes more than just a picture of our beginning. It is a unique fingerprint, a set of local conditions that point toward the wider cosmic landscape from which we emerged. While we may never be able to peer into another bubble universe directly, the specific properties etched into our oldest light are exactly what we would expect to see if we are part of a much vaster and perhaps infinite multiverse. This relentless pursuit for answers is now driving the construction of colossal new ears on the cosmos. A new generation of observatories is rising from remote mountain peaks and the frozen plains of the South Pole, engineered with a singular, breathtaking goal to listen more closely to the universe's first whisper than ever before. Projects like the Simons Observatory in the high Chilean Andes and the even more ambitious CMB Stage 4 experiment represent a quantum leap in our ability to see the invisible. They are not just upgrades, they are entirely new classes of instruments, deploying tens of thousands of superconducting detectors to capture the cosmic microwave background with a sensitivity that was pure science fiction just a generation ago. Their primary mission is to hunt for the holy grail of cosmology, the primordial B-mode polarization. These next-generation telescopes are so incredibly sensitive that they could either definitively capture the swirling fingerprint of inflationary gravitational waves, or they could rule out entire families of inflationary models, forcing us to rethink the cosmos's violent birth. But their ambition does not stop there. By mapping the polarization of the ancient light with microscopic precision, they will perform a deep census of the universe's most elusive components. They will weigh the cosmic neutrino background with unparalleled accuracy, tracing the ghostly influence of these particles from the first second of time. They will chart the expansion history of the universe with such detail that they can probe the nature of dark energy itself, testing whether this mysterious force has remained constant or has evolved over billions of years. And they will search the pristine CMB map for even more exotic fossils like the imprints of cosmic strings. These would be hypothetical, one-dimensional defects in space-time, theoretical scars from a phase transition in the very early universe, like cracks forming in ice as it freezes. Finding their signature would be a direct window into physics at energies 1 billion times higher than what the Large Hadron Collider can reach. These observatories are not merely taking a better picture, they are reading the fine print on the cosmic blueprint, searching for clauses and subclauses we never knew existed. The data they gather in the coming decade will either confirm our most fundamental theories of cosmic origins or, far more excitingly, it will reveal something entirely new, forcing us to write a new first chapter for the story of everything. This ancient light does more than reveal our past, it holds a prophecy for our ultimate cosmic destiny. The precise recipe of dark energy, dark matter, and ordinary matter, so carefully measured from the CMB's patterns, dictates the final chapter of the universe. And the data is unequivocal, with dark energy making up nearly 70% of the cosmos and driving its expansion at an ever-increasing rate. The ultimate fate appears to be a long, slow descent into silence, a scenario cosmologists call the heat death or the big freeze. This is not a dramatic explosion or a violent collapse. It is an end defined by exhaustion. As the expansion accelerates, distant galaxies will first fade to a dim red, then vanish entirely from our observable horizon, their light stretched beyond detection. Nearby galaxy clusters will be the last islands in an ever-darkening sea, but eventually, even their stars will burn through their final fuel. One by one, the stellar furnaces that have illuminated the cosmos will flicker and die, leaving behind cold, dark remnants, black dwarfs, neutron stars, and wandering black holes. Over trillions upon trillions of years, even these massive objects are predicted to slowly evaporate through a quantum process known as Hawking radiation. The universe will approach a state of maximum entropy, where energy is uniformly distributed in a vast, cold, and incredibly dilute void. There are no more temperature differences, no more energy gradients, no more ordered structures to sustain any form of complexity or life. In this final state, even the cosmic microwave background, our oldest photograph, will fade into nothingness. The photons that have traveled for over 13 billion years will continue to redshift, their wavelengths stretched by the expanding space until they carry so little energy they become fundamentally undetectable. The whisper of creation will become silence, so the story written in that first light is a complete cosmic arc, from an unimaginably hot and dense beginning to an equally unimaginable cold and empty end. Our universe's fiery birth, as revealed by this ancient glow, ultimately points toward a cold and silent conclusion. Yet this elegant cosmic blueprint is not perfectly uniform. Etched into the ancient light are a few stubborn, unexplained features that continue to puzzle cosmologists. These are the CMB anomalies, subtle cosmic wrinkles that refuse to fit neatly into our standard models. One of the most intriguing is the so-called axis of evil. This is not a physical structure, but a mysterious, unexpected alignment of large-scale features in the cosmic microwave background. The hot and cold spots seem to be subtly correlated along a particular direction across the sky, as if the universe has a preferred axis. This is deeply strange. The fundamental principle of cosmology is that the universe should look the same in all directions, a concept known as isotropy. The axis of evil challenges this core assumption, suggesting that on the very largest scales, the cosmos might have a hint of a preferred orientation. Then there is the famous CMB cold spot. This is an unusually large and strikingly cold region, a vast circular patch that is significantly chillier than the surrounding background. It is so large and so cold that it is incredibly difficult to explain as a simple statistical fluctuation. One compelling, though speculative, theory suggests it could be the imprint of a cosmic texture. Imagine the fabric of spacetime undergoing a phase transition, like water freezing into ice. Sometimes cracks and defects can form in the ice. A cosmic texture would be a similar kind of defect in the vacuum of space itself, and its collapse would release immense energy, leaving a cold spot as a cosmic scar. A third puzzle is a curious lack of power on the largest scales. The CMB's temperature fluctuations follow a specific statistical pattern, but the very largest waves, the biggest ripples in the primordial sea, are noticeably weaker than our models predict. It is as if the universe's bass notes are missing from the cosmic symphony. While it is possible these anomalies are simply rare statistical flukes in our particular cosmic neighborhood, their persistence is a tantalizing itch for scientists. If they are real features and not mere noise, they point toward a universe that is not perfectly isotropic or a history that involves new, unknown physics in its first fleeting moments. These subtle imperfections in the oldest photograph are not failures of our theories. They are the faintest of signposts pointing toward the next great frontier in our understanding of the cosmos. This faint glow is our ultimate time machine. Every time you look at the night sky, you are peering into the past. The light from a nearby star may be a few years old, while the light from a distant galaxy could have been traveling for billions of years before it reaches your eye. But the cosmic microwave background is the final stop on that journey backward through time. It is the most ancient wall of light visible to our instruments, a barrier we cannot see beyond. When we point our telescopes at this cold, uniform radiation, we are not just detecting a signal. We are directly witnessing the universe as it was an astonishing 13.8 billion years ago in its infancy. This is the oldest photograph ever taken, and it is a self-portrait of the cosmos at the moment of its own liberation. There is no older starlight, no earlier signal to find. This makes the CMB a unique and irreplaceable laboratory, a window frozen in time that allows us to test our most fundamental theories about where everything came from. It is our most direct connection to the moment of creation, the final observational frontier. Beyond this wall of primordial light, the universe's earliest moments are shrouded in a brilliant, opaque fog, a past we can only infer from the subtle clues left behind in this first, faint whisper. The narrative written in that ancient light is one of continuous, unbroken growth. Those microscopic quantum ripples, magnified to a cosmic scale by inflation, were not the end of the story. They were simply the opening sentence. For billions of years, a slow, relentless force took over, gravity. It began its patient work on those slight over-densities, the places where matter was just a little more packed together. Imagine a gentle, universal slope, an invisible incline where everything slowly rolls downhill. Dark matter, with its powerful gravity but no other interactions, formed the first and most massive frameworks, the unseen skeletons of future galaxies. Ordinary matter, the atoms that would become stars and planets, was then pulled into these dark matter scaffolds. What began as a microscopic imperfection grew, over cosmic timescales, into a dense knot. That knot attracted more gas, collapsing under its own weight until nuclear fusion ignited in its core, and the first star blazed to life. That single star was joined by billions of others, swirling together into the first galaxies. And those galaxies, pulled by the gravity of even larger dark matter structures, began to migrate toward one another, forming clusters, then superclusters, and finally the vast, intricate cosmic web we see today. This entire epoch, from the first star to the great walls of galaxies, is a direct consequence of those initial conditions. The connection is so precise that we can simulate it. Cosmologists input the exact pattern of hot and cold spots from the cosmic microwave background into the most powerful supercomputers. They program in the known laws of physics the precise recipe of dark matter and dark energy, and then they press play. The simulation runs for millions of computer hours, tracing 13.8 billion years of cosmic evolution, and when it finishes, the result is breathtaking. The virtual universe it produces is a near-perfect match for the real one we observe with our telescopes. The simulated distribution of galaxies, with its vast voids and glittering filaments, maps directly onto the pattern of the primordial fluctuations. The specific hotspot you see in the ancient background radiation might be the ultimate ancestor of a specific supercluster of galaxies we see today. This is the seamless story the CMB tells us, a continuous thread woven from the first trillionth of a second directly to the star-filled sky above us tonight. This profound fine-tuning of the universe is etched directly into the properties of the cosmic microwave background. The specific pattern of those hot and cold spots, the exact density of those primordial ripples, had to fall within an incredibly narrow window for our existence to even be possible. Consider the strength of gravity for a moment. If it had been just a fraction stronger, the gravitational pull of those initial overdensities would have been too powerful. The universe would have collapsed back on itself in a catastrophic big crunch long before stars could ever form. If gravity had been slightly weaker, the initial expansion would have been too rapid, and those crucial density variations would never have gathered enough matter to form the first galaxies. The universe would be a cold, dark, and utterly empty void. The same razor's edge balance applies to the force that drove inflation and the density of the primordial plasma. The cosmic recipe we read from the CMB is not just a random set of numbers. It is the only recipe that could have produced a cosmos rich with galaxies, stars, planets, and ultimately, observers. This staggering realization is known as the Anthropic principle. It is the idea that the universe we measure must be compatible with the conscious life that has emerged to measure it. We could not find ourselves in a universe incapable of supporting life, because we simply would not be here to ask the question. For some, this fine-tuning points toward a cosmic designer. For many physicists, however, the multiverse hypothesis offers a powerful and natural explanation. In an infinite frothing sea of bubble universes, each with its own random set of physical constants and laws, the vast majority would be stillborn or barren. They would have laws that cannot support atoms, chemistry, or complex structures. We, of course, find ourselves in one of the exceedingly rare bubbles where the numbers lined up perfectly. Our universe is not special because it was designed for us. It is the only kind of universe we could possibly inhabit. The cosmic microwave background, therefore, is far more than a fossil of light. It is the ultimate census document for our particular cosmic neighborhood. Its specific temperature, its precise fluctuation pattern, they are the local bylaws of our habitable bubble. This places the CMB at the very center of a profound debate that bridges physics and philosophy. Are we the product of a singular, unlikely accident, or are we simply one outcome in an infinite cosmic landscape where every possible reality exists? The oldest light does not give us a final answer, but it frames the question with breathtaking clarity, defining the very conditions that allow us to ponder our own existence. That baby picture of the universe became an icon far beyond the world of science. The beautiful, full sky maps from COBE, WMAP, and Planck did more than just deliver data. They gave humanity a shared heirloom, a tangible photograph of our collective origin. Here was the universe's first portrait, and everyone could understand a baby picture. This single, relatable image transformed the abstract, almost philosophical concept of the Big Bang into something concrete. You were no longer just being told the universe had a beginning. You were looking directly at the evidence, a snapshot of its fiery infancy. This power to make the cosmos accessible fueled a cultural moment. The maps appeared on the front pages of newspapers, became the centerpiece of planetarium shows worldwide, and featured in countless documentaries, bringing the grandeur of cosmology into living rooms and classrooms. This public captivation is not a trivial side effect. It fuels a fundamental human drive to understand where we came from, fostering a shared sense of wonder that transcends borders. By making the universe's story our own, this ancient light inspires the next generation of astronomers, engineers, and dreamers. It reminds us that our quest for cosmic roots is a unifying human endeavor, one that justifies the immense effort to keep looking up and asking the biggest questions of all. The oldest photograph ever taken still has its blind spots. This cosmic baby picture, for all its incredible detail, is a snapshot from a single moment in time, a barrier we cannot see beyond. It freezes the universe at the tender age of 380,000 years, but it offers no direct glimpse into its very first seconds. The cosmic microwave background confirms the existence of the dark universe with overwhelming evidence, yet it remains silent on what dark matter and dark energy actually are. We know they are there from their gravitational shadow, but their fundamental nature, the particles that make up dark matter or the engine behind dark energy, remains one of physics' greatest secrets. This ancient light is also inherently limited by our own cosmic address. It shows us only our observable universe, the sphere of space from which light has had time to reach us. It cannot tell us what lies beyond that horizon. Is our universe infinite, or is it just one bubble in a vast, frothing multiverse? The CMB offers no direct answer. It is the ultimate fossil, and like any fossil, its story is fragmented. The bone tells us the creature existed, but not the color of its skin or the sound of its call. This is not a failure of the data, but a definition of its power. The cosmic microwave background has provided us with a rock-solid foundation, answering questions that plagued cosmologists for decades. But in doing so, it has opened up chasms of even deeper mystery. It has handed us a precise, quantitative map of our ignorance, guiding the next generation of telescopes and experiments. Every profound answer it has given us simply leads to a new and more profound question, reminding us that the universe's greatest secret may be its endless capacity for wonder. All these separate threads of evidence weave together into a single, magnificent tapestry. From the faint glow of the cosmic microwave background to the distant explosions of supernova and the vast maps of galaxies, a unified story of our cosmos has emerged. This is the Lambda CDM model, the standard model of cosmology. Its name describes its two lead characters, lambda, representing the cosmological constant of dark energy, and CDM for cold dark matter. This model provides a complete cosmic biography, from a hot Big Bang and a burst of inflationary expansion to its current fate, accelerated by dark energy. The CMB is the unshakable foundation of this entire framework. It provides the essential starting conditions, the universe's initial temperature and density, and it verifies the model's key predictions with breathtaking precision. Think of it as the first chapter of a book, one so accurate that it dictates how every subsequent chapter must unfold. This concordance of data from completely independent sources is what makes the model so powerful and robust. The light from a dying star billions of years ago tells us the universe is expanding faster and faster, and the ancient whisper of the CMB explains why that must be true, revealing the precise amount of dark energy driving that acceleration. This is not just a good story, it is a quantitative, testable, and self-consistent narrative that fits observations across 13.8 billion years. The Lambda CDM model stands as one of humanity's greatest intellectual achievements, a complete history of the cosmos read from the lines of its oldest photograph. The cosmic microwave background is far more than a frozen relic from the dawn of time. It is a living document, a continuous broadcast from the infant universe that we are only now learning to fully decode. This ancient light confirms a grand narrative, a cosmos born in a searing flash from an incredibly hot, dense state. Its entire architecture, the great web of galaxies and voids, was seeded by microscopic quantum fluctuations, stretched to a cosmic scale, and then patiently sculpted by the invisible hands of dark matter and dark energy. We have learned to read this celestial script, to weigh the universe's dark components and measure its flat geometry, all from the subtle patterns in this cold, pervasive glow. It forges an unbreakable link between the frantic jitter of the quantum realm and the majestic, slow-motion ballet of galaxies. Yet for every question it answers, the CMB poses a deeper, more fundamental challenge. The Hubble tension, the strange anomalies, the very nature of the dark universe, these are not dead ends. They are signposts pointing toward physics that lies beyond our current grasp, urging us to look further. Our exploration of this oldest light is an ongoing conversation, a dialogue with the universe itself. And as our telescopes grow more sensitive and our questions more refined, we edge ever closer to answering humanity's most profound questions. Where did everything come from? What is our ultimate fate? Let this journey through the cosmos's first light be a starting point for your own wonder. The universe is speaking to us in a whisper, 13.8 billion years old. What will you ask it next? Share your thoughts on these cosmic mysteries below. Subscribe for more journeys to the edge of understanding, and never, ever stop looking up.